Hello everyone. In our last video we learned about rational expressions. We also learned how to multiply and divide rational expressions. In this video we're going to learn how to combine them. Combining is a generic term which includes both adding and subtracting. Now we already know that combining, like fractions, if we're just looking at regular fractions like containing only numbers, constants with no variables, is handled in this manner. To combine two like fractions, we basically keep the common fraction and we combine the numerators. It works whether we're adding or subtracting. So as an example, if you have 1/8 plus 3/8, we know that we keep the 8, we combine the 1 and 3, we get 4/8, then we can reduce to get 1/2. This is exactly the same way in which we can combine like rational expressions, which are basically rational expressions which have the exact same denominator. So in this case, we notice that these two rational expressions have the same denominator. We keep the common denominator, we combine the numerators. So we end up with x plus 4 over 2x plus 8. Just as in the case of 4/8, where we didn't stop there and we reduced as much as was possible, we do the same thing here. Here we notice that we can factor a 2 down here. We know that we cannot cross cancel in this manner because of the fact that there are more than one term on the top as well as in the denominator. So, and we know that we can only cross cancel when there are only factors, not terms. So but we can still do something in the sense that we notice there's a common factor of 2 down here. So we factor it out. That leaves us x plus 4. Now we can cancel the entire x plus 4 here with the entire x plus 4 up there. So this is consistent with the fact that we can only cross cancel factors, and this happens to be a binomial factor, a factor that has more than one term. In fact, it has 2 terms, but since we're cross canceling the entire factor, that's okay. So notice that the only thing left on the top is 1, so we end up with 1/2. So in order to combine unlike fractions, of course, we must first convert them to like fractions before we can combine them. So the same rule applies to unlike rational expressions as well. So whatever basically worked for regular fractions with numbers in them from our past will work now with these more sophisticated rational expressions, which are just fractions as well, but they happen to have variables in them, variable expressions. And of course, in the case of rational expressions, those variable expressions are very well behaved. Both the numerator and the denominator are polynomials. We know that in order to convert two unlike fractions into like fractions, we need to find a common denominator, right? And even though any common denominator will do, if we actually happen to find the least common denominator, that means the smallest number, for example, that this 3 and 4 go into, then the numbers that we'll deal with from that point forward will be much smaller. It'll be much more efficient as an operation. So what we're going to do is we're going to come down here and we're going to find the least common multiple of 3 and 4. Remember, the least common denominator is just the least common multiple of all the denominators involved. Here we only have 2. Even if we had 2,000 fractions we were combining, the same rule would hold. We would need the smallest number that all of those denominators go into. In this case, we know that number is 12. So what we're going to do is we're going to try to turn both of these denominators into 12. To turn 3 into 12, of course, we need to multiply by 4. But we can't just do something to the denominator of a fraction. We have to instantly do the same thing to the numerator. So we multiply the 2 by 4 as well. To turn the 4 into the common denominator of 12, we need to go ahead and multiply it by 3. And of course, we can't just do it to the denominator. We have to do it to the associated numerator as well. So we multiply that by 3 as well. And of course, this is why we get away with doing this, because we're basically multiplying by 1 over here as well as over here. So the fact that 2/3 has been multiplied by 1 tells you that this 2/3 and this 8 over 12 must have the same exact value, and they do. And the same thing goes for 1/4. We're just multiplying it by 1. It's going to look different. It's going to look like 3 over 12, but if you punch into a calculator, you'll get exactly the same value. We can see that real quickly just for demonstration purposes. Let's go ahead and clear this. Notice that if we divide 1 by 4, we end up with 0.25. And if we divide 3 by 12, we also get the same thing. So the value is the same. They look different, but they have the exact same value. Now, now that we've turned these two unlike fractions into like fractions, now we can just keep the common denominator and combine the numerators. So we get 8 plus 3 over 12, which is 11 over 12. As simple as this is all you need to understand to be able to handle combining rational fraction combinations as well, or rational expression is the better way of putting it. So to combine unlike rational expressions, we'll utilize a very similar technique, as we'll see in a minute. Now 3 and 4 are very simple numbers, so it was extremely easy to find their least common multiple, meaning the smallest number that both 3 and 4 go into. However, if the numbers get larger, it would be good for us to have a procedure in place that helps us find the LCM in a very systematic way, which doesn't require much guessing. So let's just go ahead and see how it will work out. We'll say 30 and 45. Okay, so just as we did in the case of GCF, we are going to find the prime factorization of both numbers, and then we'll see where that takes us. Now notice that for 30, we start by dividing by the smallest prime number that goes into it, which is 2. So 30 divided by 2 is 15. We repeat the process. We ask, what's the smallest prime number that goes into 15? That, of course, is 3. We divide, we get 5. Now, what's the smallest prime number that goes into 5? Well, since 5 is a prime number, remember, the only prime number that's going to go into a prime number is, I'm going to leave a blank. I think I heard you say it, itself, right? So, because remember, when you have a prime number, there are only two numbers that go into it, itself and 1, right? But listen to the question. I said, what is the smallest prime number that goes into a prime number? And 1, we don't consider to be a prime number. So when you deal with a prime number, the only prime number that's going to go into it is going to be itself. So once you hit this 1 down here, that means you're finished. You have the prime factorization on the left here. So 30 can be written as 2 times 3 times 5, just like that. Now, if we take care of 45, we start with 3. Remember, with 45, a lot of people jump to 5, but it's much nicer if you start with the smallest prime number that goes into any given number. That way, your prime factorization will be nicely ordered from the smallest factor to the largest factor. So when a number is divisible by 5, meaning it ends in a 5 or a 0, you should always try to see if it's divisible by 3 as well before you jump to 5. So for 3, you add the digits, like here, 4 and 5, they add up to give us 9. If 3 goes into that sum, so if 3 goes into 9, which it does, that means it also goes into 45. So if 3 goes into the sum of the digits of a given number, 3 will also go into the number itself. So we write the 3 here. We divide 45 divided by 3 is 15. We write it on this side. Now, again, what's the smallest prime number that goes into 15? That'll be 3 again. 15 divided by 3 is 5. And now we're down to a prime number again. What's the smallest prime number that's going to go into this prime number? Of course, itself. And we get to 1. Now, this is actually why we didn't want 1 to be considered a prime number, because otherwise the procedure for generating prime factorization would never end. Because here we would say 1, 1, 1, 1. You know, that it would be an endless loop. So that's why we purposely designated 1 as not a prime number. All right. So we can see that 45 is 3 squared times 5. Okay. Now, when we were trying to find the GCF of two numbers a few videos back, if you remember, for the GCF, the procedure was multiply the lowest powers of only the common factors, okay? Now, for the LCM, since we're looking for a number that is big enough so that both of these numbers go into it, we're not going to be multiplying the lowest powers. We're actually going to be multiplying the what? Exactly, the highest powers. And remember, you're looking for a number that both of these factorizations go into. That means you don't just multiply the common factors, the highest powers of the common factors. You're going to multiply the highest powers of all the factors. That way, you're going to end up with a number large enough so that both of these numbers go into it. So we first of all identify all the factors that are involved. We notice there's 2, there's 3, and there's 5, right? So for each one, we locate the highest power that we can see in these two factorizations, and these factorizations need to be written in exponential form for our procedure to work. So notice that the highest power of 2 that is in either factorization is just 2 itself. For 3, notice the highest power of 3 is 3 squared. For 5, notice they're the same, so we just take one of them. We don't need to take both. You remember, just locate the highest power of every factor that you see, bring it here, and multiply it out. And then you will get your LCM. So this is the procedure for finding the LCM. We will multiply the highest powers of all the factors that are in the prime factorizations of the numbers involved. All right. Well, in this case, we're dealing with only 2 numbers, so we say in both prime factorizations. So notice 2 times 5 is 10, times 9 is 90. All right. Let's make the numbers a little bit larger just to get the feel for how nice and efficient this procedure is. So you may have even been able to guess the 90 for 30 and 45. I think you'll agree that guessing the least common multiple of 420 and 792 will be a little bit harder, correct? But we have a procedure that will give us that LCM beyond the shadow of a doubt. So here we go. We're going to start by finding the prime factorization of 420. Remember, write 420, draw a line, then ask yourself, what's the smallest prime that goes into 420? Of course, that's 2 because 420 is even. So 2 goes into 420 210 times. Ask the same question again, what's the smallest prime that goes into 210? 2 again, you divide, you get 105. 2 won't work anymore, so we notice 1 plus 0 is 0 plus 5 is 6. So therefore 105 is divisible by 3 since 6 is divisible by 3. So we start with 3, so we go 105 divided by 3 is 35. Now we can't handle 3 anymore because 3 plus 5 is 8. That is not divisible by 3, so 35 is not divisible by 3. But 5 will certainly go into 35 7 times, and now 7 is a prime number. What's the smallest prime number that goes into a prime number? Itself. So, and then we'll get to this one and we're finished. So there's the prime factorization of 420. 420 is 2 squared times 3 times 5 times 7, just as we do here. This is the prime factorization in exponential form. 792, we start with 2 again, we divide, we get 396. We notice it's still even, so we can divide by 2 again, we get 198. Use 2 again to give us 99. Now we have to go to 3. Notice 9 plus 9 is 18, which is divisible by 3. Therefore, 99 is divisible by 3. So we divide by 3, we get 33. Repeat again by 3, we get 11. Now we've hit a prime number, and of course, the smallest prime number that goes into a prime number is itself. And then we end up with that last one, and we're finished. All right, so we can see that 792 is 2 cubed times 3 squared times 11. 2 cubed times 3 squared times 11. So notice that we have a procedure in place. We're going to multiply. To get the LCM, we're going to multiply the highest power or highest powers of all factors. So notice the factors that are involved. Here are the factors: 2, 3, 5, 7, and 11, right? These are all the factors that can be found in either prime factorization, right? So we need to take, for 2, the highest power that we see. Notice that would just be what? 2 cubed. For 3, we take the highest power, which is 3 squared. For 5, the highest power that we see is just 5 itself. For 7, same thing. And for 11, also the same thing. The highest power we can see in either factorization is just 11. Then we just need to multiply that out. You can do that on a calculator. And there you have the prime factorization of, the least common multiple of 420 and 792. You can verify just to satisfy yourself that both of those numbers will go into that number. So here's a good quick check. So we can make sure because if it doesn't, we've made an error, right? But if they both go into it, it doesn't guarantee that it's the least common multiple, but it definitely guarantees that it's a common multiple. So it's at least that much of a check. So we're going to divide that by the first number, 420. Actually, let me make this cleaner. Let's just start from scratch. I don't know why I hit the enter button the first time. All right, so we want 27720, and we're going to divide that by 420. And when we do get a perfect 66. So we know 420 goes into the LCM 66 times. Notice you can see that very nicely, because here is the LCM. It's right here, right? All right. I will be right back. So when we look at 27,720 right here, we know that 2 squared, right? So all but one of these, and 3, so one of those 2 factors of 3, and 7 are comprise the 420, right? So what's left is a 2, a 3, and 11. And when you multiply 2 times 3 times 11, you get 66. So you could actually do that division without a calculator if you know the prime factorization of 27,720. So now let's go ahead and repeat the process, but this time we're going to change the 420 to 792. So like so, and we get 35. So we can see how both of those numbers go into the LCM perfectly. 792 goes into it 35 times. 420 goes into 27,720 66 times. All right, so there we have, and you can see how powerful the procedure is. It can handle a number no matter how large it is. This is the kind of algorithmic approach that you would program a computer if you wanted to teach it how to find the LCM of 2 numbers. So let's remember the procedure for finding the LCM of a finite number of numbers or expressions. The exact same procedure works for expressions as well. We basically find the LCM by writing all of them in prime factored form, and not only that, but we use the exponential version of the prime factored form, and then we multiply the highest power of all factors. That's it. If we can just do that, we should be in possession of the LCM. Just wanted to quickly remind you, the procedure for finding the GCF was closely related. To find the GCF, we multiply not the highest, but the lowest powers of the common factors, okay? So with LCM, you multiply the highest power of all factors, but for GCF, you multiply the lowest power of only the common factors. So there's a really important relationship between these two quantities, the GCF and the LCM. I wanted you to see the interaction between them. It's a beautiful diagram that relates them. So given any 2 numbers, we're just going to use 30 and 45 here as an example, right? There are 2 numbers associated with that pair of numbers, or you could actually have more than 2 numbers here. You can have 10 numbers, 10,000 numbers. There's always going to be, given any finite group of numbers, there are going to be 2 numbers of interest associated with those numbers. One is, what is the largest number that goes into both of them? So this diagram beautifully shows going into, using arrows from the GCF to each of the numbers. So that's what we mean by GCF, the greatest common factor. It's the largest number that goes into both of the numbers, and if these were expressions, it would be both of the expressions, and if there were more than 2, then it would be the one that goes into all of them, no matter how many items you have under consideration. So the LCM is the other extreme. So this was the greatest number, or the largest number that goes into both of them. The LCM is actually the smallest number of all the ones that both of them go into. Okay, so that's the least common multiple, and we're going to be realizing this important relationship in a few examples and see how they interact with one another. So these are the two most important quantities when it comes to trying to do some kind of gain some kind of an understanding from a group of numbers. We want to know what is the largest number that goes into all of them, and then what is the smallest number that all of them go into. And we remember the procedure. For the GCF, we're going to multiply the lowest powers of the common factors, and for the LCM, we're going to multiply the highest power of all the factors, because remember, that's got to be big enough for all the numbers to go into. This one can't be too big. It has to only contain common factors, because otherwise it won't go into one or the other. So you have to have only common factors in here, and you also want the lowest power, because otherwise, again, if you took the higher power, let's say you took 3 squared instead of 3, notice then it wouldn't go into this number. So that's why you have to have the largest power, the smallest power of only the common factors. Notice if you took a factor that is not common, like if you took the 2, right, and brought it here, well, it wouldn't go into this number. So that's why we need to multiply the lowest power of the common factors. For the LCM, multiply the highest power of all the factors. So now that we know all that, let's go ahead and find the GCF and LCM of these two expressions. Notice they're not just plain numbers anymore, they're expressions, but we can basically use the same procedure. So let's go ahead and put them in consistency with the previous problem. We'll just put them in the middle here. So we have 10x cubed y squared z, and we have 15 x to the 4 y squared w squared. So one thing I would like to do is I would like to quickly go ahead and look at the prime factorization of 10 and 15. So 10 we know is 2, 5, 5, 1. 15 we know is 3, 5, 5, 1. So I'm going to replace the 10 here with 2 times 5, and the 15 with 3 times 5. So I'm trying to find the GCF and LCM of these two expressions, and now I have just the product of factors. Remember, these numbers can be treated just like factors as well. So let's see, we'll start with the GCF, which of course you know is the largest expression that's going to go into both expressions. So we know from the procedure that we need to multiply think of the apparent contradiction here. It appears like, but it's not. You understand why it's true, but it's kind of nice to remember it this way. For the greatest common factor, you actually multiply the lowest. So this apparent contrast, remember, for the greatest common factor, you multiply the lowest power of only the common factors. So one thing we can do is just go ahead and bring only the common factors here first, then we'll put the right exponent on them. Okay, so let's start with just the factors that are common. So what are they? Well, we can see there's a 5 in common. There's also an x in common. Remember, we're not worrying about the exponents yet. We're just bringing the common factors right now. And we notice y is common, right? But there's no z in this one, so it's not part of the common factors, and there's no w in this one. So that's not a common factor here. So that's it. We only have 3 common factors, 5, x, and y. So now we're going to take the lowest power of each of those factors and bring it here to multiply. So we notice that for 5, the lowest power is just 5 itself. For x, between x cubed and x to the 4. Which one is lowest? X cubed. So we're going to use x cubed. For y, we notice that the lowest power, when we compare y squared and y squared, they're equal. So the lowest one there is just itself. So y squared. And there it is. We have the GCF. Now, I know in this section we're mostly going to be using the LCM, but this relationship between the GCF and the LCM is so important and so beautiful, I thought we should be dealing with it. All right, so now we're going to go to the other extreme. We're going to find the lowest expression, the simplest expression in some ways, that both of these expressions go into. So in other words, we're looking for the LCM. Now remember, for the least common multiple, we have a procedure as well. We're going to multiply the highest. Notice, for the least common multiple, you multiply the highest power of, this time, all factors. So why don't we do this? Why don't we first just bring a copy of each factor without worrying about the exponents yet. So we can see there's a 2, there's a 3, there's a 5. So we need 2, we need 3, we need 5. We notice there are x, we have x, y, z, and w. Make sure you have represented every single factor that there is, right? There's no child missing, right? Okay, so now we go through, and for each one of these, we pick the highest one and bring it here. So for 2, of course, the highest power of 2 is just 2 itself. For 3, it's also just 3 itself. For 5, same. For x, between x cubed and x to the 4, what's the highest power? X to the 4. For y, between y squared and y squared, what's the highest power? Of course, just y squared itself. For z, you have the highest power is just z itself. I guess if you want to be a little consistent and go alphabetical here, I would put the w first. Doesn't matter though, remember. It's because of multiplicative commutativity. I could have put it the other way around. This just looks slightly nicer. All right, otherwise WZ is exactly the same as ZW in mathematics. Remember, that's called the multiplicative property of multiplication. The commutative property of multiplication, or for short, multiplicative commutativity. All right, so we took care of y. For w, of course, the highest power that we see is w squared. We already took care of z, but I wrote it here, and that's the highest power of z that we see as well. So now all we're going to do is we're going to simplify this by just multiplying it out. 2 times 5 is 10, times 3 is 30. So we get 30. X to the 4, y squared, w squared, z. And that is our LCM. All right. There it is. So it's a very simple but a very important procedure. Both of these are extremely important numbers and expressions associated with a group of numbers or expressions. When you start to understand numbers at this fundamental level and expressions at such a fundamental level, that's when you really start to gain some insight and some depth as far as mathematics is concerned. All right, so here we're going to find the GCF and LCM of these two polynomials. Now, of course, before we do so, because remember the procedure for both involves what? Factors, right? So before we can do it, we're going to go ahead and factor both of these expressions. So we notice the first one is a trinomial. We can factor it as x plus 4 times x plus 1, for instance. Or we could have put the 1 here, 4 there, makes no difference. We notice first times first is first, last times last is last. The inner product is 4x, the outer product is x, and they add up to give us positive 5x. So we factored this correctly. Now we factor this one. We notice that one is a difference of squares, so it's just going to factor as x plus 4 times x minus 4. So now let me go ahead and put those factored forms here. X plus 4 times x plus 1 and x plus 4 times x minus 4. Remember, we're looking for the GCF and the LCM. Let me move these a little bit. All right, so we're looking for the greatest common factor, GCF. So remember the procedure. Once we have written both expressions or both numbers in fully factored form, then we're going to multiply the lowest power of the common factors. So we look in here to see what factors are in common. Remember, these are all binomial factors, but they are factors. So we notice that the only factor in common is the x plus 4. So those are not. So they're not going to be part of the GCF. There's only going to be the x plus 4 involved. And which power of it? Of course, just the first power. So in other words, there it is. That's all the greatest common factor is, the x plus 4. Now for the LCM, remember we're going to multiply the highest power of all factors. So notice the factors that are involved here. We have x plus 1, x plus 4, x minus 4, right? We don't need to count x plus 4 twice. So basically, we're just going to multiply all of those to get the LCM. The highest power of x plus 1 that we see is just x plus 1. The highest power of x plus 4 that we see is just x plus 4. Sometimes students make the mistake, they put the x plus 4 twice and they use x plus 4 squared. That's not necessary. Remember, you look at the factorizations and you simply pick the highest power that's available. Now, the highest power of x plus 4 in either factorization is just x plus 4 to the 1 or just x plus 4 itself. So we bring x plus 4. And then we also need x minus 4. There we have it. Now we have just found the LCM. And here we found the GCF. Notice two very simple, very important procedures. All right? And very important quantities here and expressions. All right, so make sure that you understand this before we proceed. So here we're trying to find the GCF and LCM of 3 expressions. Go ahead and try this on your own for sure before you rejoin the video. Pause it and then come back. All right, notice that we have 3 expressions. Let me go ahead and write them next to each other here. And the last one is 9 times x squared plus 3x plus 2. So we're going to take each of these three expressions, 3 times x squared minus 1, I should say 3 times quantity x squared minus 1, and then x squared plus 2x plus 1, and 9 times quantity x squared plus 3x plus 2, and we're going to factor them as much as possible. So with the first one, we can see that we have a difference of squares. So x plus 1 times x minus 1 is the factorization. Don't forget to carry the 3. For the middle one, we can see that's a perfect square trinomial, right? Remember the rule? F squared plus 2FL plus L squared equals quantity F plus L squared. Here, F is x, L is 1. So basically, that expression right there is the square of x plus 1. So we get quantity x plus 1 squared. The last one is a trinomial, so we'll factor it like a regular trinomial. The second one, of course, was of course a trinomial too. It was just special because it was a perfect square trinomial. This one is just a regular trinomial, quadratic trinomial. So we go ahead and try x and x, and it's a very simple one, maybe 2 and 1. Let's see, first times first is first, last times last is last, inner product is 2x, outer product is x, they add up to 3x, so we've done it correctly. All right, so let me, since they're kind of large, let me write them in a different fashion this time. Let me write them like this. So here are our 3 expressions in factored form. So we have that, we have x plus 1 squared, and we have 9 times x plus 2 times x plus 1. So first we're going to find, I'm going to write it in this direction for space's sake. So we're going to find the GCF, which is of course the greatest expression that will go into all of them. And then we'll also find the LCM, which is the smallest or the simplest expression that they will all go into. So, and remember the procedure. For the GCF, we're going to multiply the lowest power of only the common factors. And for the LCM, we're going to multiply the highest power of all factors. Because remember, we need something large enough for them all to go into. So notice for the GCF, first of all, look what factors are in common, right? Well, I see x plus 1 in common. We left out a 1 here. So we notice there's x plus 1 here, x plus 1 here, x plus 1 here. And there's no other factor that we see in all 3 of them, right? That's the only common factor. So the GCF is x plus 1. And which power of x plus 1 do we take? Well, the lowest power. So between x plus 1 to the 1, x plus 1 squared, and x plus 1 to the 1, what is the lowest power? Of course, x plus 1 to the 1, which we write as just x plus 1. For the LCM, we need all the factors present, and then we'll take the highest one of each. So a good idea here, since 3 is a prime number already, right? But if we really want to stick to principles, let's go ahead and write 9 as 3 squared, right? That's the fully factored form of 9. And let's go ahead and bring that down here too. This will help us find the LCM more easily. So notice that we have not a common, but we have a factor of 3. There's a factor of x plus 1. We're not worried about exponents right now. We're just taking what factors are in play. There is a factor of x minus 1. and there's also a factor of x plus 2, right? And notice that now we'll go through, and for each of those factors, we'll take the highest one for the LCM. So for 3, we notice that between 3 and 3 squared is the winner, right? How about x plus 1? Which is the highest power of x plus 1 that we see in these 3 expressions? Of course, this one, x plus 1 squared. For x minus 1, there's only one of them, so that's going to be the one that's going to be there. And for x plus 2, notice there's only 1, 2, and the exponent is 1, so that's all we need. All right, so finally, we'll just clean it up. So we'll write it as 9 times x plus 1 squared times x minus 1 times x plus 2. So there we have the LCM on the right here. And here we have the GCF on the left. Just to demonstrate, look at the LCM. Notice how they all will go into it, right? So let's test it. Here's the LCM, 9 times x plus 1 squared times x minus 1 times x plus 2. And notice how 3 times x plus 1 times x minus 1, which is the first expression in factored form, notice how it goes into it. 3 goes into 9 3 times. X plus 1 goes into itself once, and into x plus 1 squared, x plus 1 times. And x minus 1 cancels out completely, and we end up with 3 times x plus 1 times x plus 2. The point is, we don't get any fractions or anything like that. So we say that 3 times x plus 1 times x minus 1 goes into 9 times quantity x plus 1 squared times quantity x minus 1 times quantity x plus 2, exactly 3 times x plus 1 times x plus 2 times, okay? This is like saying 2 goes into 6, what? 3 times. So this expression goes into this expression that many times, okay? That was just demonstrating with one of them. You can see how x plus 1 squared will certainly go into the LCM, and how this last one, 9 times x plus 2 times x plus 1, also goes into this expression, which is the LCM. All right, so now we get to the good stuff. We'll now go ahead and combine rational expressions. Now, this one is easy because we can see the denominators are the same, right? All right, so we'll go ahead and keep the common denominator, combine the numerators. Simple. This is just using the a over c plus b over c equals a plus b over c. You want to write the real general version of that, put plus or minus, because it works with subtraction too. So you end up with x plus 4, and of course we know we can't cancel like that because these are terms, but we can try to factor the denominator, right? Don't forget that's a plus 4. We accidentally wrote minus 4. So we're going to factor x squared plus 5x plus 4. We're going to get x plus 1 times x plus 4, right? Notice first times first is first, last times last is last. Inner product is x, outer product is 4x. They add up to 5x. Now, I notice that I know I can't cancel out one of more than one factors, but what if both of them are considered to be one binomial factor? Can we cancel out like this now? Absolutely. And what are you left with on top? A 1. a 1 here too, but that one is going to get absorbed once we multiply it by x plus 1. So we basically end up with 1 over x plus 1. That's how you handle a problem like that. Simple, but still requires fundamental skills. All right, so here we notice we do not have like fractions, so because their denominators are different. So basically, we need to find the LCM first, or the LCM of the denominators, which is called the LCD, right? So what is the least common multiple of x and x plus 4? So a very common mistake is for people to think, oh, it's just x plus 4, because look, x is in there, so we don't need to, go ahead and write it again. It just goes, that's going to be the LCM. That's completely incorrect. Let me give you an example. What if you have 1 over 3 plus 1 over 3 plus 4? Just imagine a number for that x, right? Notice, what's 3 plus 4? 3 plus 4 is 7. Does 3 go into 7? It doesn't. So what would you have to do if you wanted the LCD here? Well, you would have to multiply 3 by 7, right? In other words, 3 by 3 plus 4. You have to multiply those. So that's exactly what we're going to do here, just by the principles we found. Remember, we're looking for LCM, so we're going to do what we always do. We're going to multiply, of course, if everything is in factored form, which it is. Those are very simple expressions. So we're going to multiply the highest power of all factors. The highest power of x is just x. The highest power of x plus 4 is just x plus 4. So we multiply that. There we have our LCD. So now we can do this. We can write our LCD here, because that's what we would like both of these denominators to turn into, right? So now ask yourself, what is this denominator missing? What do I need to do to it so that it becomes like this common denominator? And I think even if you look at it from just a purely artistic point of view, you can see that what's missing is this x plus 4 factor, right? So that's exactly what we're going to do. We're going to multiply the x by x plus 4. But remember, we can't just do that, can we? Because that's a fraction, and if we've just done something to the denominator of a fraction. So we have to do the exact same to the numerator. So we're going to multiply the top by x plus 4 as well. Now, in this other fraction, right, we have a denominator of x plus 4, and we want to turn it into this common denominator. So again, go into your artist mode. What's missing? X, right? So we need to multiply the x plus 4 by x. And if we do that, we have to exactly do the same thing on the top, right? So notice that we now end up with x times x plus 4 as this denominator, and x times x plus 4 as this denominator. So these two denominators are now the same, and they're both this. So all we have to do now is combine the numerators. Well, the new numerators, right? The adjusted numerators. So we end up with x plus 4 plus x, like so. So notice that that ends up being 2x plus 4 over x times x plus 4. Now, when you get to this stage, you should always try to see if there's more factoring possible, which would enable more cross cancellation. And of course, here we notice there is no canceling in this manner because these are more than one term. The only thing we can do is see if we can factor. And if you do that, you end up with 2 times x plus 2 over x times x plus 4. We noticed that the factoring didn't do us any good, right? Because that didn't create any common factors we can cross cancel. So oftentimes we will just go ahead and leave that as the final answer. But this is a perfectly legitimate version of the final answer as well. You could even leave this or that, and they're both correct. As far as aesthetics and possibly which one looks simpler, we would probably normally go with this one. All right, definitely try this one before you rejoin the video. Pause, try, come back. All right, so as you notice, these are unlike fractions because, or if you want to really be technical, unlike rational expressions because they don't have identical denominators. So we need to find a least common denominator, which is of course going to be the LCM of those two expressions. And of course, remember, for the LCM, we multiply the highest power of all factors. Here we have two binomial factors, meaning two factors which have each two terms, right? So the highest power of u minus 1 that we see is just itself, and the highest power of u plus 1 that we see is itself. So all we have to do is multiply those two themselves by one another, and we end up with the LCM, which is the LCM of the denominators, which technically speaking is now the LCD. Remember, the LCM of all denominators is called the LCD, the least common denominator. All right, so let's write our LCD here, u minus 1 times u plus 1. And let's go ahead and make both of those denominators turn into this. Let's do what is needed to be done so that these turn into this, right? So you can see this factor is missing that factor to become the whole LCD. So we're going to make sure you parenthesize. So we're going to multiply that by u plus 1. And we always remember that anything we do to a denominator, we need to immediately do to the associated numerator as well. And we can see that this denominator is missing a u minus 1. So we're going to go ahead and multiply that by u minus 1 and immediately do the same on the top. So now we have the exact same denominator on both. So now we have like fractions. We started with two fractions that were not alike. By a clever move, we have turned them into like fractions. Now we're going to go ahead and just keep the common denominator and combine the new numerators, right? So we're going to get u plus 1. Let me go back to the other color, blue. Okay, so u plus 1 minus, be very careful here not to just write minus u minus 1. That's an extremely common mistake. That's why I don't recommend that you try to distribute this as you see it. Just write it down. It's like negative 1 times u minus 1. And now safely go ahead and distribute the negative 1. So notice we end up with u plus 1 minus u plus 1, right? See, u plus 1 minus u. Negative times negative is positive, so we get positive 1 times 1, which is 1. And down below, we still have u minus 1 times u plus 1. We're almost done. We notice that those two terms are going to cancel out because they're opposites. And the two 1s are going to combine to give us 2 over u minus 1 times u plus 1. And if you notice, there's nothing else that can be done. There's no cross-canceling possible. Nothing else we can do. No factoring. They're all simple factors. We're finished. We box it and we are done. Make sure you can handle it before we proceed. All right, so here we have one of those special situations, if you call from our previous video, which we call the f minus L over L minus f situation. If you remember, when you have those, that's like saying 3 minus 7 over 7 minus 3. Remember, 3 minus 7 is negative 4, 7 minus 3 is 4. So those two can definitely cancel out, but not cleanly, right? They leave a negative 1. So that is always the case when you have a difference of two terms on the top and the reverse difference on the bottom. So whenever you have that scenario, you can safely cross cancel and put a negative 1. That's when it comes to what the value of that fraction is. When it comes to the relationship with respect to fractions like this, where we're trying to find an LCD, we're not going to need this fact. I wanted to remind you of this because of the work that we did in the previous video. But here, I need you to remember something else that we did when we were trying to prove this fact is true. If you remember, we said f minus L can be written as negative L plus f, and then we can factor out a negative 1 to leave us L minus f. In other words, you can just write minus L minus f. So in other words, f minus L is the opposite of L minus f, right? So if I were to take one of these two fractions and multiply the denominator by negative 1, I should be able to get the other fraction. So let me just work on this one. So this is the trick we'll use to figure out this problem. So we go ahead and multiply it by negative 1. Remember, that means you're going to distribute negative 1 like that. Notice negative 1 times negative x will be x, and negative 1 times 3 will be negative 3. So when you multiply 3 minus x by negative 1, it turns into x minus 3. Look, try it down here. Negative 1 times 3 minus x. You get negative 3 plus x, which of course you can always write as x minus 3. So, but don't forget, you can't just multiply the negative 1 on the bottom there. You have to multiply it on the top as well. So watch what happens. So now the 3 over x minus 3 doesn't change at all because we're not doing anything to it. But notice here you have negative 5 times negative 1. So now that's going to turn into plus 5. And also down here, remember, you multiply negative 1 by 3 minus x, which is going to be what? X minus 3. So you see how much the problem changed? Now we have two simple like fractions. So we keep the common denominator, which is x minus 3, and we combine the numerators. So we get 3 plus 5. So finally, we get 8 over x minus 3. And you're done. So be careful with these. You don't need to do the extreme version, which I've seen a lot. Students make the mistake of just multiplying x minus 3 by 3 minus x. X minus 3 times 3 minus x is a common multiple or a common denominator of this problem, but you can certainly see it is not the least common multiple or the least common denominator. So, but when we do this trick, we'll end up using the least common denominator, which is just going to be the same denominator that they both are. All right, so make sure you can handle that little twist in the road, and we'll move on to another one. All right, go ahead and try this one on your own. It's very, very simple actually. Remember, you're going to need an LCD, which you're going to write down here. Then you're going to make these fractions or these denominators become like the LCD, etc. So make sure you pause the video and try that. Okay, so we need to find the LCM of these two expressions. Basically, 15 I'm going to write as 3 times 5 x squared y, and the other expression is 5x y squared. So we need the LCM of those two expressions, right? So notice, we know the procedure: multiply the highest power of all factors. So what's the highest power of 3 that we see? Just 3. What's the highest power of 5 that we see? Just 5. What's the highest power of x? X squared. Highest power of y? Y squared. So there it is, multiply it out, 15 x squared y squared. That's going to be the LCD. So now we need to make each of these denominators turn into that, right? So what would be missing here? Well, if you look at it, there's only just what? One y missing, right? So that's what we're going to do. We're going to multiply this fraction by y, the denominator, so we have to do exactly the same on the top. Remember? What's this missing in order to become this, right? In other words, what do you have to multiply this by to get this? Well, one quick way of figuring that out, just divide this by that. That's one way you can do it. Or just reason it out. You need a 3 to make the 15, so times 3. You need an x to make the x squared. And that's all you need, because you already have the y squared. So just don't forget that 3x needs to be multiplied on the top as well. So now we're going to notice that the denominators are now exactly the same, and they're exactly this. So now we can just combine those new numerators, which are 7y minus 9x. And that's it. That's all we have to do. We are finished. Why? Because there's nothing else we can do. We know we can't cross cancel because these are terms, and we know that there's no common factor here. So it's just 1. So factoring out the 1 isn't going to do us much good, so we are basically done. All right, so here's our last one for the road. Remember, we need to go ahead and start by factoring each of those denominators in order to help us find the LCD. So you should definitely pause the video, try this. By now you should be able to handle this, and then come back and see if our answers agree. All right, so I'm going to rewrite the first fraction as 1 over x times, remember, I'm just going to factor the GCF, so x times x minus 2 plus 2 over, so now we're going to factor this trinomial. It looks like f squared minus 2fl plus l squared. What should give it away that this could be a perfect square trinomial is the fact that the first term is a perfect square and the last term is a perfect square. So we notice that if we just bring that down here, we notice that L is basically X, and I'm sorry, F is X, and L is being played by 2. So we notice that this is just going to be X minus 2 squared. Because remember, when we have that expression, that factors as F minus L squared, quantity F minus L squared. All right, so this trinomial here is going to factor as well. Of course, what if you didn't see this? What if you didn't see that that's a perfect square trinomial? Well, no problem. You could still just go ahead and factor it like trinomial factoring. You need 2 expressions here whose product is x squared, so x and x, and 2 expressions whose product is positive 4, so 2 and 2, but you want the inner product and the outer product to be negative 4, so we're going to make them both negative, and that's it. So you can see, once again, you realize, oh, that's quantity x minus 2 squared. All right, so the middle fraction is quantity x minus 2 squared at the denominator position. And also the last one, we notice it's a difference of squares. That one, I hope you have it really down by now. That's just going to factor as x plus 2 times x minus 2. Now we're going to find the LCD. So let me go ahead and erase some of this stuff that we don't need anymore. Of course, the good thing about the video is that it's not lost forever. You can always go back to it if you need to. All right. So remember, we're going to, first of all, need all the factors involved. I noticed that I have a factor of x. I'm not worried about exponents right now. I just want the factors. I notice I have a factor of x minus 2, and I also have a factor of x plus 2. So now, what is the highest power of x that I see? Well, there's only one x, and that's its own highest power, so that's it. How about x minus 2? Well, I notice x minus 2 here, x minus 2 squared here, and x minus 2 here. Of those 3, the highest power is right there. So we need x minus 2 squared, and x plus 2 is only appearing here, so that's going to be the highest power, and that's what we have right there. So now we're going to just make a unified fraction with that LCD. And now we're going to make sure that each of these denominators becomes like the LCD. So what's missing from this denominator in order for it to become the LCD? X is already there. One factor of x minus 2 is there, and there is no x plus 2. So obviously what's missing is one factor of x minus 2 and also a factor of x plus 2. And we remember that anything we do on to a denominator, we got to do on the top. So we're going to multiply by x plus 2 times x minus 2 on the top as well. For this middle fraction, we notice that what's missing is an x and an x plus 2. So that's how we're going to take care of it. We're going to multiply it by x times x plus 2. We don't forget that we have to do the same on the top. So we're going to multiply the top by x times x plus 2 as well. How about this last denominator? What's it missing compared to the common denominator? Well, notice it's missing one factor of x minus 2. It's also missing x. So that's what we're going to do. We're going to multiply it by x times x minus 2 And of course, we don't forget the numerator, like so. All right, so now we notice that all fractions have this denominator. Yeah, it may not look like it, but look, this is just x times x minus 2 squared times x plus 2, right? Look at this. That's x times x minus 2 squared times x plus 2, yes. And look at this one. That's x times x minus 2 squared times x plus 2. So they're all the same. Now we're going to combine the new numerators that have come about. So we notice that we have, from the first fraction, we have x plus 2 times x minus 2 plus, from here we have 2x times x plus 2. Notice I'm not going to do anything in my head right now, try to distribute or anything like that. I'm just going to write it. Yes, it's a little bit more writing than probably you would like, but it's going to get you the correct answer. That's what's important here, right? Like so. Now we go ahead and simplify as much as we can. So notice here we have a product of two conjugates. Remember those? F plus L times F minus L. That's going to be F squared minus L squared. Remember? One of the nicest formulas we deal with. All right, so we get x squared minus 4 plus, now we're going to distribute the 2x, so we get 2x squared plus 4x minus, now we're going to distribute the 3x, so we get 3x squared plus, that is minus 3x squared plus 6x. And then the whole thing over x times x minus 2 squared times x plus 2. So now we notice that we have x squared plus 2x squared, which is 3x squared, and then a negative 3x squared here. So what happens? You guessed it. Those three cancel out. And we notice that 4x and 6x give us 10x. So we have 10x, and then we have the minus 4 over x times x minus 2 squared times x plus 2. Now, we notice, yeah, there is a common factor of 2, right? But if you factor that out, what's it going to leave you? Let's see, down here. It leaves you 5x minus 2. Notice that will not be able to cancel with anything, so you'll be stuck anyway, and that would be it. So, given that we've tried and there's no more cancellation possible, we go ahead and box it, which should also wrap it up for this video. I know it was on the long side of things, but sometimes it's necessary, unfortunately. All right, so I hope that you've learned much, and go ahead and practice, and be safe until our next video.